up until 1697, human beings as a species don't really fully understand gravity. We know that things on Earth accelerate at negative 9.81 meters per second squared. That's known at the time. What we don't understand at that point in time is that gravity is actually the force that kind of governs the cosmos, keeps planets orbiting, moons orbiting planets, things along those lines. So in 1697, Isaac Newton essentially discovers what is known today as the universal law of gravitation. If you're interested in the backstory of that, I suggest the video regarding the rivalry between Isaac Newton and Robert Hooke, which I'll link down below. But at this point in time, Isaac Newton has this thought experiment in it. He considers a cannon firing a cannonball, as you can see here. And what he starts to realize is that if you fire that cannonball a little bit faster, it's going to fall a little bit further before it kind of, curves down in its parabolic projectile path and hits the ground. So he thinks again, well, if I fire it even faster, it'll go a little bit further. And he begins to say, well, let's fire it faster and faster and faster. And while we're at it, let's zoom out. So he says to himself, well, if we go ahead and we place this cannonball on top of a mountain and we zoom all the way out, you fire this cannonball at some speed, becomes a projectile and it hits the ground. If you fire a little bit faster, it will go a little bit further around the Earth. A little bit faster, it'll go a little bit further. And he starts to realize that if you ever fired it fast enough, you could actually get this thing to start to orbit the Earth. So it's weird to think about, but if you fired it fast enough, it would be falling towards the Earth at the same rate at which the curvature of the Earth is occurring. So he develops what's known as Newton's Law of Universal Gravitation, which means for any two objects, not just the Earth and some mass on the Earth, if you would like to determine the gravitational force between any two objects, you're going to use Fg equals G m1 m2 over r squared, where the Fg is the force of gravity in newtons. G is what we call the gravitational constant. You'll be given that value. You don't have to memorize it, but it's 6.67 times 10 to the negative 11th. M1 is the mass of one of the objects. M2 is the mass of the other. And R is the distance between the centers of those objects. So if we wanted to calculate the gravitational force between that cannonball that's being fired in this example and the Earth, we would have to use the distance from the center of the Earth all the way up to the center of the cannonball. But anyway, Isaac Newton discovers that gravity, the very same gravity that we feel on Earth, on the surface of the Earth, is responsible for the moon orbiting the Earth orbiting the sun, etc. Essentially, the moon is just constantly falling towards the Earth, but because it's moving forward through space, as it's curving towards the Earth in an attempt to fall towards it, well, it just happens to be falling at that same rate that the Earth curves away underneath it. So the moon is actually perpetually falling towards the Earth, but the Earth keeps curving away, and therefore it kind of continues in perpetuity. That was a pretty groundbreaking realization that the very force of gravity that we kind of encounter on the surface of the Earth is in fact the same force that governs celestial bodies in space. Granted, we can't just use 9.81 because that's a very specific value for the surface of Earth. So this equation here allows us to analyze gravitational forces throughout the universe, which is why it's such a powerful equation. All right, so in the next video, I'll show you a few examples of how we apply this and how we analyze multiple objects. What if we have more than just two objects? How do we analyze that situation? But it's important to understand that the gravitational constant will always be that 6.67 times 10 to the negative 11th, and the rest of that equation is simply the masses that are interacting with one another, as well as the distance between their centers. Because any two masses, not just the Earth and some other mass, any two masses will exert a gravitational force on one another. So your body and your laptop right now, or your pencil and your calculator, any two objects with mass will attract towards one another, and this is the equation we can use to calculate that.